Okay, let's start. Do you have any questions? Sorry, give me a moment here. My iPad's not connecting. All right, so from last time, we discussed section 4.3, right? Which is about recurrent and transient classes, right? Communicating classes of the Markov chain. And the point is, right, that basically a Markov chain will have recurrent and transient states, right? And the states, if they communicate with each other, then they all share the same properties, meaning that if a state is transient and it communicates with another state, and that the other state will also be transient, and so on and so forth, right? The point is, well, before we went into these sections, I said that 4.3 and 4.4 are about long-term behavior, right? Of a Markov chain. And by long-term, right, I mean as t goes to infinity. And it's not, I guess, it's not quite clear yet based on 4.3 what long-term behavior means. But here you can see, right, for example, so what I mean is like 4.4 will actually be where it's kind of very clear on what this means, but you can kind of see the starting idea here, right? Because with 4.3, what's the message? The message, if you think about it in terms of, right, long-term behavior, will be that for a Markov chain, right, it will never, right, stay in a transient class in the long run, right? That's the very definition of a transient class. So a Markov chain will always escape, right, from transient classes. As t goes to infinity. In fact, right, so that's sort of like one property of a Markov chain, that if it's in a transient class, it won't stay there for long, right? It won't stay there forever. As t goes to infinity, you'll guarantee that it will escape the transient class. A Markov chain a Markov chain, right, will eventually be in one of the recurrent classes. As t goes to infinity, right? And so, again, I'm not saying that these are deep statements. In fact, they sound rather trivial, right? Because that sounds like obvious. The goal or the use of 4.3 is to tell you, right, to help you to be able to tell which states or which class are transient and recurrent. Okay, so 4.3 gives you the tool to identify, right, these recurrent and transient classes. But it's not, well, I guess when we look at this, we immediately see that this is not enough details, right? What further questions should we ask if we care about the long-term behavior of a Markov chain? So as I mentioned, right? So additional questions. These are very natural questions to ask. The first one may be related to question B or property B, right? A Markov chain will eventually be one of the recurrent classes. You probably might ask which recurrent classes. Will the Markov chain be in? Okay, so that's probably the first question you ask. For example, right? I mean, again, let's use this as, just as the example to think about these questions, but it doesn't have to, right? So suppose we have a 5-state Markov chain like this. Right, something like this. Then you see that with respect to this question, which recurrent classes will the Markov chain be in? It's this question, it might sound, I don't know, reasonable on paper. In practice, the only answer you can give is it depends, right? It depends on what? It depends on your initial position. It depends on your initial condition. For example, right? But this doesn't mean that we cannot say we don't have, anything to say about this statement, right? For example, we can elaborate on this. The one thing that you can know, right, that we talked about before, is that if you're in a recurrent class, you will never escape from a recurrent class, right? Remember that there is a problem, I think, problem number 16, right? that talks about how a recurrent class is a closed class. So if the initial condition is such that you started from the recurrent class, then you will be in that recurrent class for the rest of the remaining time, right? So that's one thing we can say. If we start, right? If the Markov chain starts in a recurrent class, it will stay there, right? For all t. And this is just, another way to say a recurrent class is a closed class, right? It's closed. And, right, problem number 16 will have more to say about this. Let me see if that's number 16. Yep. So there's nothing else we can say about this, right? If you start in the recurrent class, you stay there. But I guess the question then is, if you start in a transient class, right? If you start at a transient class, so you will escape from there, right? If you start at state 5, you will escape from state 5. But which recurrent class will you be into? And here, right, I think the answer is also obvious, right? At least with this transition matrix, the way we wrote it down is equally likely, right? Equally likely that the Markov chain will end up in one of these recurrent classes. No, because it's both 1/4 and 1/4, right? It's both 1/4 and 1/4. But then you also see, right? You have to look at the actual transition matrix to be able to tell which recurrent class you will end up at with what kind of probability. So that's all we can say, really, right? It depends on the actual transition matrix. We cannot make an abstract statement with more details than that. So if the Markov chain starts in a transient class, then we need to look at, right? The transition matrix P to be able to tell. So all in all, A is not really a bad question to ask, but not much we can say, right? Beyond this kind of like preliminary observation. Well, what can you ask then, right? Well, so alternatively, right, or actually, the question you can ask is actually along this way. Once you're in the recurrent class, right, a recurrent class, because you think about it like this: if you're in a transient class, then after a finite amount of time, you will get out of it, and you will settle right into one of the recurrent class. That's a theme. So we might as well assume that you are already in a recurrent class, because you will be there, right? One way or another. So the question then is, once you're in a recurrent class, right? Once you're in a recurrent class, then how often does it visit a certain state? Now, we have to be careful, right, on what we mean by how often, because the sort of the cheesy answer is, well, infinitely often, because all states, right, in a recurrent class are recurrent by definition, and a recurrent state, right, Markov chain will revisit a recurrent state infinitely often. So that's not what we mean, because that's trivial. What we mean is a relative, right, proportion. So how often here refers to the proportion of time. Okay. For example, suppose that the Markov chain end up in this recurrent class. Then again, because we wrote this down, it should be super clear that the Markov chain would spend 50% of time on state 0 versus 50% of the time on state 1, right? That's super clear. There's nothing, to doubt about that. But just in case you think, well, isn't that obvious? Well, that's just because we, put something very easy down. What about something like that? Right? You see, we just changed the first row to some other weights that also add up to 1. And if you want, right, let's change this as well while we're at it. Now I hope, right, that you see that the answer is no longer obvious. Right? Of course, there's still an answer. But let's say once the Markov chain is in this recurrent class, what's the proportion of time it spends at state 0 versus what's the proportion of time it stays at state 1? And then you see again, right, of course, it has a lot to do with these numbers, because it depends on how often, right, you go into state 0, let's say, from some other states. Sorry, this is 0 to 0, 0 to 1, 1 to 0, right? So here, it depends on how often you go to state 0 from other states, but also, I guess it depends on how likely you will go away, or you're guaranteed to go away from state 0, right? Yeah. So, okay, so yeah, let's say that, right? It depends on how likely it is that you go into state 0 from some other states, etc. So anyway, but this is a valid question to ask. The answer is not obvious, but it's there, right? How often does the Markov chain stay in a certain recurrent state? Now, one remark that we make here is the following. Once the Markov chain is in a recurrent class, right? Because we know from the first observation that it will be in some recurrent class. The point here is that a recurrent class, if you look at carefully, is like a mini Markov chain, right? It's a closed world. A recurrent class is closed, right? And if you stare carefully, well, it's not that it has to sum exactly to 1 along the rows of a recurrent class, but almost, right? So the point is that basically, once we're in recurrent class and we're in like a mini Markov chain, right? A mini world in and of itself. In other words, as far as this question is concerned, meaning that once you're in a recurrent class, how often you spend time in a certain state, this question might as well be applied to, we can assume without loss of generality, we can assume that the Markov chain is irreducible, right? Remember, irreducible means there's only one communicating class. I mean, I guess maybe recurrent as well, right? Because there is, right, irreducible Markov chain that is transient, the one-dimensional random walk. So, but what I'm saying is, like, you might as well assume that it has only one recurrent class, because a recurrent class, right, is like a mini Markov chain in of itself. And again, right, this might seem trivial, but the word state here, right? So we kind of switch it back and forth, right, between the word state and the word class. Sometimes they're kind of interchangeable because, for example, right, a recurrent class and a recurrent state are very much connected because, of communication, right? On the other hand, it makes no sense to talk about how often does a Markov chain visit a certain recurrent class. Do you see why? So if we ignore this, we talk about how often does a Markov chain visit a certain class, certain recurrent class. It makes no sense. Do you see why? Well, the reason is pretty simple, right? It's because a Markov chain will only visit one recurrent class. It will not visit multiple recurrent classes during, let's say, one path, right? Because once a Markov chain is inside recurrent class, it will not get out. Therefore, during a trajectory, a Markov chain will only visit one recurrent class. So the question of proportion of time it visit a certain class won't make sense, right? And just to be clear, right, what do we mean by proportion of time? Here's what we mean, right? For example, if you look at the path, you see something like this: 0, 1, 1, 0, 2, 0, 1, 1, 2. Let's just say that. Then proportion of time, it stays in state 1, which we denote as pi 1, will be something like 1, 2, 3, 4 out of how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I count, right? 3, 9, right? It's approximately 4, 9. We understand, right? That's what we mean by proportion of time. And therefore, right, this question makes no sense with the word recurrent class. So if you're inside a class, you will not get out. All right. So now, this question, right, clearly cannot be answered with the tool 4.3. We need more tools. The third question, right, as I mentioned before, is that, how to say this? The third question is a little bit subtle, but it talks about the stability. Does the distribution of the Markov chain converge? All right, so what do I mean? What do we mean by this? What we mean by this is, right, that suppose that eventually it will settle into a recurrent class. Then, at each point in time, you can write down the probability that the Markov chain will be in state 0, right? For example, you can say something like probability that x1000 is equal to 0. Probability x1000 will be 1. That's the distribution of x1000 once it settles, right, into, let's say, this recurrent class with states 0 and 1. But then, of course, you can ask probability of x, let's say, 1001, right? And clearly, you see that these two should not be the same or may not be the same. Why would they, right? There's a transition matrix influencing, right, the movement from one step to the next step. However, it's conceivable right? And the I guess I'm not sure if the technical language, the technical word here is well mixed, but basically the idea is under some circumstances, and it's more often than you think, the Markov chain has gone through many movements, and so that basically this distribution settles down to a stable pattern, meaning that the difference between these two values is minimal, or you can say is almost equal to zero. That's what it means to converge, right? This sequence, right? And you understand, right? And 1,000 here is just an arbitrary large number. Basically, this sequence of numbers will start to converge to a stable target at stable value. Does that happen at all, right? If it does, that's wonderful. And we want to know what the limit is and how do we get it? Okay. So these two questions, and by the way, this question, the way it's asked, and in the view, right, in view of the fact that the Markov chain will settle into a recurrent class eventually, we can also assume that the Markov chain is irreducible. So what I'm saying is, and maybe I'll give you sort of like a preview, but in 4.4, right, this kind of Markov chain won't show up as much. So we spent 4.3, right, in identifying, right, whether a state is recurrent or transient, or identifying a recurrent class, a transient class. When we come to 4.4, we almost always deal with a recurrent Markov chain overall, right? We don't have a division into so many sub classes. I mean, again, we may when we do a problem, but the sort of the spirit of 4.4 will focus on one single Markov chain, or we will focus on one single recurrent class, right, inside a Markov chain, and asking questions B and C. So any question before we continue with 4.4? All right. So the title, of course, is long-term, long run. I guess it's the same word. Proportions and limiting probabilities. And just like 4.3, we have to start out with a bunch of definition before we can start saying something meaningful. All right, so I guess the first order of business is to improve on some of the concepts, or yeah, improve probably is not the right word, but be elaborate more on some of the concepts of 4.3. The first, right, is to recall the concept of f sub I, right? F sub I is a probability that this Markov chain will revisit state I for some, right? So that's the word is for some, starting at I, right? And this is exactly the key, right, for us to distinguish a recurrent class or versus a transient class. Now we will make this concept a bit more general by saying, well, we don't have to limit this to state I, going back to state I, right? So we can say probability, right? You ever, right? This is the probability that the Markov chain ever visits state J starting at state I, okay? So of course, J here can be equal to I, in which case we'll return to F sub I. And so the first thing we observe is the following. If I is recurrent and I communicates with J, then Fij is equal to 1. All right, so in English, what are we saying? And by the way, right, what should we compare this to? Of course, we should compare this to the, the very definition of recurrent class, right? Sorry, recurrent state. I is recurrent if F of I is equal to 1. This is definition, right? There's nothing to prove, I mean, for this statement, this part. But from here, right, we can make it more general by saying that if a state is recurrent and it communicates with another state, then it's guaranteed that the Markov chain will visit the other state starting from the recurrent state. In fact, right, well, you see, if you isolate these two statements, and it says that I and J are in the same recurrent class, correct? And this Fij equals to 1 means the state is guaranteed, sorry, the Markov chain is guaranteed to visit it. So in a way, if you think of the spirit of this statement, it's saying that a Markov chain is guaranteed to visit all recurrent classes, all recurrent states inside the recurrent class. Right. So once again, sound obvious, but no, we need some proof, right? So for example here, it says that, right, if the Markov chain ever settles, let's say, into this class, that it will visit both state 0 and state 1. It will not be the case that it will only stay at 0 and not visit state 1, which is very obvious here, right, for this transition matrix. But when we blow up to like 1,000 states, then it might seem a bit interesting, right? Because how do we know that once it's in a recurrent class, it will not miss, let's say, state 501? Or if you will, right, try to apply this to some other interesting case that you know about, like the one-dimensional random walk when p equals to 1/2, right? It's recurrent. Then this statement says that, well, if you are in a one-dimensional random walk with symmetric random walk, then no matter how far out the state is, let's say state 1,000,000 or state 1,000,000,000, the Markov chain is guaranteed to visit it starting at state 0. It will get there. Again, sounds believable, right? Because, you know, there's a positive chance that the Markov chain will go from 0 to state 1,000,000,000. But when you think of the minuscule, right, probability for any path to get there, that's a different question. But of course, again, right here, Fij plays on the notion of infinite horizon, right? It doesn't care how long it takes to come back as long as you come back. And sort of that's why, right? is kind of guaranteed to visit. It doesn't care how long you have to wait. Okay, but well, enough clarification. Let's see if you can prove this. How do you prove this? Okay, so let's think about this, right? First of all, what do we know? The first thing we know, of course, is that J is recurrent, right? From the previous section. Now, so I hear J there, right? You know that if you start I, you are guaranteed to come back somehow, right? Of course, not in this sense that I returns immediately to I. You have to wander around and come back. But this guarantee, start at I, return back to I, means what? Means that if you ever go to J, right, which is, you know, which has a positive chance to happen, right? Then from J, you are forced to go back to I. Does it make sense? So we talked about this before, right? Basically, the chance of escaping, the chance of never returning from I, will at least accommodates the possibility that you go to J, and then from J, never go back. Hold on. So let me see how. Like that. Do you understand? Right. The chance of the probability of escaping from I and never go back includes the possibility of going to J and then never return to I, right? And so therefore, if we know, for example, that f sub I is 1, then this number is, and of course, right, this is bigger than or equal to 0 because these are all probabilities, so we're just multiplying non-negative numbers. Now, if we know f of I is equal to 1, then of course this is equal to 0. And of course this is equal to 0. But because PIJ raised to t power, right? P to a t power raised at ij entry is positive. That means this must be equal to 0. Which means FJ is equal to 1. So notice what have we achieved? We have achieved something in reverse, meaning that if we look at the chance of escaping from I, then it sort of influenced or it reached the conclusion about FJI. Because, you know, sort of like, because eventually that's about returning to I from the node J. But of course, right, I and J here are symmetric, and we know J is recurrent, so we can turn this argument around and looked at 1 minus f sub J, P to the or you can change the P to S if you will, Ji 1 minus Fij. And there you have it, right? Because we know F sub j equals to 1, j is recurrent, and then P to S, Ji is positive. This must be 0. That's the Ij equals 1. Any question? Okay. So the next thing is to talk about, and again, right? So this is elaboration on the notion of probability of returning. But the next one will be an elaboration of the notion of recurrence. So the next one is about something called positive recurrence versus no recurrent. Okay. So there are more than one types of recurrent, and we'll see why. So in order for this to talk about this, we want to look at, we want to make the following definition. So tau sub I, define tau sub I as the first time such that the Markov chain returns to I given that it starts from I. Let me see. Yeah. And of course, you need to have one step because otherwise you will immediately go back, right? So there you go. So basically, it's just, this is called, right? We have seen this before, right? This is called a stopping time, first return time, right? If you start at a state, how long does it take for the Markov chain? How many steps does it take for the Markov chain to return to that state? So now this is a random variable, okay? And let's distinguish this from, let's say, the probability, like Fi, right? And Fij, things like that. So let's say tau I versus Fi, because they sound suspiciously similar, but they're not, right? First thing to note is that tau I is a random variable and Fi is a probability, right? Tau I takes on value 1, 2, 3, etc. It's really the geometric random variable, right? Sorry, is it? It's a number of steps, right? Yeah, exactly. It's the geometric random variable, right? With success probability Fi. No, not Fi. Anyway, so at each step, right, you look at the first time you return to state I, but Fi is a probability, right? And of course, its value is between 0 and 1. I mean, yeah, it could have probability 0, but yeah. Okay. But what does it mean for, let's say, if a state is, if Fi is less than 1, right, strict less than 1, then that means I is transient. What does that translate to in terms of tau I? If Fi is less than 1, that means I is transient. What does it translate to in terms of tau I? Oh, sorry. I think I know what I was saying wrong. Tau I is not a geometric random variable. That's where I was getting a hiccup. Tau I is not a geometric random variable because each time you don't get a independent trial, right? From n to n plus 1 is basically depending on where you are at time n, and then you transition to time n plus 1 based on the transition matrix. So tau is just waiting, right, for something to happen. But the trials, right, the movement from one step to the next are not independent and are not necessarily identically distributed, at least in terms of like from I to not I, etc. So anyway, so but here, right, if I is transient, what does it mean for in terms of tau I? You can see that what it means is probability that tau I is infinite is positive, correct? And what is actually probability tau I is infinite? It's exactly 1 minus fi. Do you understand? Well, what does infinity here mean? Infinity here means, because it's the first time you return to state I. Infinity means you never return, you escape, right? So tau is infinite is exactly probability of that is probably you escape. Okay, so far. So if fi is equal to 1, that means I is recurrent. That means probability tau I is finite is equal to 1. Okay, so far. However, right, well, so this is just kind of clarifying the notion of first return time, right, with probability of returning. And by the way, right, let me just say this, the textbook, the notation of the textbook will use n sub I for tau sub I, all right? That's what they use. And I want to clarify because, right, for us, for me, I will use n sub I for the number of visits to state I, starting at I. So just so you know, if you read the textbook and you see n sub I, they refer to this, right? Notation is super important here, and you don't want to get confused. And I try to stay with the notation of the book as much as I can. But notation tau is actually a very common notation to denote first returning time. And so for me, actually, this is more suggestive than using n. N seems to me to be counting up something. So anyway, right, just so you notice. So I will use, right, this notation when I do the lecture. If you read the textbook, just pay attention that what you're looking for may not mean the same thing as what we discuss in the lecture in terms of symbols. But anyway, so let's continue. So the definition of a positive recurrent state is the following. State I is, positive recurrent if expectation of tau I is finite. And that's enough. State I is no recurrent if I is recurrent but expectation time is infinite. And so first thing is you want to kind of stare at these two statements and wonder what's going on, because why do they distinguish these two phenomena? And you see, right, it all is based on the expectation of the first returning time. So notice, what do they both have in common? What they both have in common is that probability of tau I is finite is equal to 1. Okay. Well, why? And I kind of said, right, I kind of say, well, here you don't have to say that I is recurrent within the definition, even though if you want to be careful, you can state it out loud. The reason is the following. If a random variable, and we're talking, in general, can take on infinite value with a positive probability, and of course, we're talking about a non-negative random variable, right? Because this is time. So this random variable will never take on negative value. So if we have a non-negative random variable, and it can also sometime with positive probability take on infinite value, it doesn't take much imagination to see that its expectation must be infinite. So a transient state, right, expectation of the first returning time is infinite. That, right? Because there's sometimes it will never return, however small probability. So the contrapositive of that is, if this is finite, then this must also be 0. And that's why we don't have, when meaning probability of tau I is finite is 1. That's why we don't have to put that statement there. Okay, so far? On the other hand, why can we distinguish this? The reason is, right, there are random variables that are finite with probability 1, but can have infinite expectation. Okay, so there are random variables that are finite most of the time, all of the time, but can have infinite expectation. What's an example? Maybe let's ask you this. Find an example of a random variable x such that probability is finite is equal to 1. So maybe let's focus on non-negative random variable, right? Non-negative. So maybe that, right? Sorry, let's throw that in here, right? Non-negative, but its expectation is infinite. Oh, by the way, right, when we say find an example, and let's say in a more advanced situation like this, find may or may not be, or should be, sort of like a construction example too, meaning that you may not have seen an example like this before, meaning you don't want to search for it in the family of random variables you know about, because most of all of them have expectation, right? Have finite expectation. So you kind of have to, you want to think about it more. We want to think about outside of those examples, or construct an example. All right. Any example? So, of course, right, you first of all, you should notice that for a random variable to have infinite expectation, it cannot take on finitely many values, meaning that it cannot have a discrete support. Sorry, it cannot have a finite support, right? Because if it only takes on finitely many values, then the integral, right, or the sum over finite many values is finite, meaning we have to play with infinite number of values. And then when you think of infinite number of values, then something like an infinite sum, right, a series comes to mind. So it's just really playing with an infinite with a series, right? Infinite series. And what series do we know that sum to infinite? Well, the harmonic sum comes to mind, right? But we're looking at this as an expectation, right? So this is expectation. Clearly, this cannot be a probability because the sum is infinite, so there's no way to normalize it down to one. But it's if we look at this as an expectation, meaning that this is going to be the sum from n times 1 over n squared, right? And it's very clear what we're looking at. Because here, this is like the probability, right, that we're looking at. So this is x, and this is probably x equals to x. Almost, right? Because we do also know that the sum of 1 over n squared is not 1. So this is a like, right? So the actual probability is what? The random variable x will be, prob x equals to n is, let's say, c times 1 over n squared, where c is such that the sum, right, of c 1 over n squared is equal to 1. Right? Because if we have this, then we have a legitimate random variable satisfying this. Now, you might be curious on what the value of c is. Does anyone know? Well, c will be, right, 1 over the sum of 1 over n squared, whatever that is. We do know, right, the sum of 1 over n squared is finite. And that's the whole point. But if you look into the literature, or if you ever took the course Math 421 or some Fourier series, you will know that this is pi squared over 6. So c 6 over pi squared. Not that it matters, right? Just some number. But here's an example for you that there's a random variable with infinite expectation. Okay. And I mean, so this is just a more like an abstract example, but closer to home, which we will prove, is the one-dimensional random walk. All right. The one-dimensional random walk, the symmetric random walk, exactly, is no recurrent, meaning that it will, so if you start at state 0, you're guaranteed to return to state 0. Or for that matter, if you are at a state, any state, you're guaranteed to return to that state. It's just that you, on average, you have to wait an infinite amount of time before you return, which is super interesting to think about, right? You're guaranteed to return. It's just going to take infinite amount of time for you to return. this is connected to I forgot, but some sort of like, in case you think that's not something you care about, because what's so exciting about returning to a state. If you attach that to like a reward, right? You can devise a game where you show the customer that the customer is guaranteed to win, right? You can now, we can make a game like a random walk where you give the customer some money if the state ever return, right? The Markov chain ever return to the same state. It sounds like a great game because you you guarantee money, right? You show the customer that with probability 1, they will win money. What you're not showing them is that it will take an infinite amount of time on average for them to claim their money. So you can pocket, right, the entrance fee and never have to pay out on average. So whatever, right? So something like that to think about in terms of these interactions. But so before that, let us see. Yeah. So let's do a proposition before we prove. If I is positive recurrent, hold on. Do we have enough tool? You know what? So I'm gonna put it down here, right? And we will prove it later because the tool for this proof it has not been developed or has not been discussed yet. But I just want to put it down here because it's sort of like related to what we discussed so far. If you have a positive recurrent state and it communicates with another state, then the other state is positive recurrent. And of course, that's true with no recurrent, right? Because you can negate the statement and get no recurrent, right? So basically, same thing here. If I is no recurrent, I communicate with J, and J is no recurrent. So basically, once again, we see that thing there, right? That positive recurrence or no recurrence is a class property. So in fact, okay. So just from this point of view, you see that we're kind of elaborating, right, on the concept of 4.3. So let's take a look at this matrix again, even though it's not relevant here. But basically, a Markov chain will be broken into sort of possibly three types of classes: transient, recurrent, but within recurrent, there are two subtypes: positive recurrent or no recurrent. Okay. Now you can be guaranteed that can you? Yeah, I think you can be guaranteed that a finite Markov chain must be positive recurrent. A finite Markov chain must be positive recurrent. Can we say that? Yeah, I think so. But I wonder how. So let's put down another proposition. It's kind of obvious, but irreducible recurrent Markov chain must be positive recurrent. So in other words, if you are looking for no recurrent, you have to look at the one-dimensional random walk, right? So anyway, so these two propositions will prove it, but you know, we need some tools. So let me see what to do next. All right. So anyway, maybe let's see if you have any question first before we continue. All right. So the first thing we want to do is a example, right? So this is an example of just a random variable. But what about a Markov chain, right? That's no recurrent, because we're just making this example out of outside context of a Markov chain. So you want to ask, right? Because here also is connected with this. If this proposition is true, meaning that if a finite irreducible recurrent Markov chain must be positive recurrent, then you have to look at an infinite Markov chain, right? For an example of something that's no recurrent. So we mentioned that before, right? So example of a no recurrent, ouch. So the symmetric 1D random walk is no recurrent. Okay. So in other words, if you trust this proposition as well, that means that if no recurrent is a class property, then the one-dimensional random walk, right, is irreducible. So all it means is that you just have to prove one state is no recurrent. Again, I mean, I know that we haven't proven this yet, but based on these propositions, then that's all we need to do. So let's ask you to do that, right? So this is quiz 3. Prove this. How would you prove the state 0 in a symmetric random walk is no recurrent? All right, so what does it take here? What are we dealing with? Or what does it take to prove something is no recurrent. So first of all, notice, right, that we did prove that 0 is recurrent, right? Meaning that we prove that a symmetric random walk is recurrent, right? Remember, we have two proofs for it, using either the returning probability, where we show is equal to 1, or, right, we also use the Stirling's approximation, right, to show that the Stirling approximation, I think, has to do with the number of visits, right? We show that the number of visits must be infinite, right? But yeah. So, but now what we need to do now is to prove it's not recurrent. So basically, then that has to do with tau I, right? Oh, sorry, tau 0. Tau 0 is the first time that the random walk returns to 0. And so we need to show that expectation tau 0 is infinite. Okay. And how do we do so? So we need to look at then probability tau 0 equals to k, right? Because we need to then analyze this expression and show that somehow it's equal to infinite. But anyway, right, how do we look at the probability that tau 0 goes to k? So remember, right, this is actually very similar to the proof of the Stirling approximation, right? So basically, the first thing, sorry, maybe we should do n here, right? Because we will specify. The first thing we note right away is that it's only possible to return to state 0 after an even number of steps, right? You cannot return to state 0 starting at 0 with an odd number of steps. So and of course, right, for any right path, there's also a left path that's exactly the same, symmetric, right? So we only have to look at the right path and multiply by 2. But for example, right, if you want to think about what's probability that tau 0 equals to 2? What's the probability the first time, right, you return to state 0 takes 2 steps? Well, simple, right? Either go right and go left, or go left and go right. Each of those was 1/2 squared. Correct. But what about then equals to 4? Well, you see that basically then you have to, so here's a thing, right? You could go 2 steps right, 2 steps left, right? Or you can go to, well, how to say this? You may think that you can go to state 1 and then 0 and 1 and 0, right? That also returns to 0 in 4 steps, but that won't count, right? So basically what I'm saying is this: within the 4 steps analysis, you might have 2 scenarios. The first one is go to right twice and go left twice. That's 4 steps. Or go to 1 and then back, 1 and back. That's 4 steps. However, the second scenario, the 0, 1, 0, sorry, 1, 1, 0, right? 1, 0, 1, 0 scenario. This won't work. The reason is because you have already visit state 0 in the second step, right? Tau 0 is the first time you return to state 0. So you cannot, right, have visited 0 before that. Does that make sense? So probability of tau 0 goes to 4. The only way that can happen is that you go to the right twice and you go to the left twice. And the 2 here is because you can do exactly the same on the left. Okay, so far? All right, so, well, can we generalize then? Maybe let's take a look at one more thing. What's the probability you can take 6 steps? Well, here, right, here actually is tricky. Here you see that, well, you can take 3 steps to the right and 3 steps back. However, you can also take 2 steps to the right and then return to 1 and then go back. This is okay because you will not, right, visit 0 before time 2, before time 6. Does that make sense? So you can do something like 1, 2, 1, 2, 1, 0. Or 1, 2, 3, 2, 1, 0. So there are 2 possible paths you can take. Okay. And so on and so forth. Meaning that I'm just saying that the analysis, right, of going, how to say this, taking 4 steps so that exactly, right, the first time, so exactly that 0 is the last step you visit, given that, right? So the sequence in between can repeat, but cannot go back to state 0. That would be, you can develop this, right? But let me say that the combinatorics there you have to think about. Okay, so let me just put it like that. So my point being is that, yes, you can prove this using the calculation of expectation of tau 0. But unlike, maybe let's say unlike the other proof where you look at p to the n 0, 0 for the, recurrent statement, there you don't care how many times you have returned to 0 in between. But here you do care. All right, so we're going to prove it using another way, which is also the same way that we'll prove these two propositions. Okay, and that will be a much better way to do this problem than analyzing the distribution of tau zero. Any question? All right, so here comes, so far, right, we just talked about the sort of concepts. Here comes a first important, let's call it theorem. Long-term proportion. Okay, spent at a state. Proportion of time. So it's the following. Let xt be a Markov chain that is irreducible and recurrent. All right. Then let pi I. So basically, we already have a Markov chain that's irreducible and recurrent. That means that for any state, right, you are guaranteed to return to that state. And there's only one class, right, within this Markov chain. Let pi I be the proportion of time. The Markov chain stays a state I. So first of all, let us state what that means. So remember, right, we have this notion of n sub I, which is the number of visits to state I, right? Which is a sum I n from 0, right, to infinity of indicator function xn equals to I starting at I, right? So pi I is something related to ni like this. So pi I will be the limit as n goes to infinity of the sum of n equals 0 to capital N of indicator function. Okay. So in words, what is this? This, this, right, is the number of times the Markov chain stays at state I, but up to a finite horizon, right? Which is the example that I give you, I guess at the beginning of today's lecture, right? Basically, you look at the first 1,000 steps, and you look at how many times, right, among those 1,000 steps, the Markov chain is in state I, and you divide by 1,000. That's kind of the approximation of pi I. Of course, then you push that to 1,000,000 steps, 1,000,000,000,000 steps, right? Then that's the long-term proportion, right? That a chain stays at state I. Now, the one thing that is first of all questionable, or if you ever take a real analysis, then when you see limit like this, the first question you should ask is, how do we know? That the limit exists? Okay. So just because you write down something using the notion of limit doesn't mean that the limit exists. Okay. So there's that. But I'm just kind of referring to you on what it means to refer to a proportion of time. But the theorem by itself should at least give you some idea on why the limit exists. But here's a result. Then pi I is 1 over expectation of tau. In other words, right, sort of, this is a shorthand to say the limit here exists n equals to this value. Okay. Any questions so far? So that's sort of like the significance of looking at, right, expectation of tau I. And by the way, right, this implies one thing. So the immediate implication is if I is no recurrent, then pi I will be 0. And of course, if I is positive recurrent, then pi I is positive. So the proportion of time that the Markov chain spends at a no recurrent state is 0. So that's another way to look at, right, these things, that basically if a state is no recurrent, then you're guaranteed to revisit it. But it takes so long that for all practical purposes, you might as well say that the chain spends 0% of time at that state. But if it's positive recurrent, then yes, not only that the chain will guarantee to be revisit, but also it's positive proportion of time spent at that state. Okay. So how do we prove this statement? The proof of this statement, right, is sorry, 1 second here. Okay. So the proof of, right, saying that this limit exists and is equal to this will play on a very interesting idea that sort of like switch, right, between space and time, if you will. So how to explain, right, that this is true? Well, when you think about it, here's an alternative way to write pi I. An alternative way to write pi I is the following. Well, if you look at time 0, right, and look at tau I, which is the first time it takes to revisit state I, right? So you're at state I times 0, right? So this is tau I. So the first instance of tau I, let's say tau I sub 1. Then, right, it might take a little bit longer to revisit state I. So this is tau I sub 2, right? So these are the inter-arrival time. All right. So if you look at this sequence of times, then the proportion of time the state spends. So for example, right here, right, how long? So in this picture, for example, right, let's look at this picture. And this is a finite picture, so it has to be extended to infinity. But, you know, just the same thing here, right? We kind of look at a finite amount of time and then stretch to infinity. In this picture, right, what is the proportion of time the state has spent at state I so far? So the Markov chain. Well, so based on this picture, right, you see it's clearly has been there 4 times, right? And well, I guess, yeah, right. But then how long has time elapsed? How long has time elapsed is going to be, right? Remember, right? It's the number of visits over how long time has elapsed. And how long time has elapsed is tau I sub 1 plus tau I sub 2 plus tau I sub 3. Okay, so far? So the claim is that in general, right? And you see, the story will just continue, right? Suppose here's another time, it's tau I sub 4, right? So the claim is that pi I will be the limit as little n goes to infinity of n over the sum of I from 1 to n tau I. Sorry, this is weird. Hold on, let's not call it that. Okay, like that. Okay, so technically speaking, let me see here in the way I draw this picture. It doesn't matter. So technically speaking, right, the way I draw this, the way I state this, it should be n plus 1. You know, it's sort of like because the first time we visit, right, we also give it 1 time. But you see, right, it doesn't matter because this will go to infinity. So 1 over that, it goes to 0. So it's really equal to that. So, okay. And so let's kind of explain. Again, what does this represent? This represents the number of visits, right? And because the chain is guaranteed to go back to this state. So that's why the number of visits just keep counting up. But the denominator represents the random times it takes to pick up that many visits. So of course, right, dividing those two together, number of visits over the number of time, the amount of time that has elapsed, give you the proportion of time spent in that state. But the interesting thing about this formulation is sort of like it uses the random inter-arrival time to define, right? So here, what's random is the time it takes to rack up that many visits. The definition above here, the time is fixed, is a capital N. It's the number of visits within that horizon is random, which is, well, take your pick. To me, I naturally think in this mode, meaning that when I think proportion of time, I take a window, right, time window, and then I count how many visits along the time window divided by that length. But if you switch things around, you should acknowledge it, or you must acknowledge that this is an equivalent way to define it. Meaning that, right, you fix the number of visits, but then you look at how long it takes for that to happen. Okay. Now, why is this a more promising, or exactly is the way to look at this concept? The reason is because, right, here you have something to back you up. If you divide both numerator and denominator by n, right? Like that. Then this is the sum of IID random variable, right? This is time to visit, second time, third time, fourth time, etc. These are IID random variable. So this is a sum IID random variable divided by n. You have a lot of large number to back you up, which will become, and you have the limit also exists because of law of large numbers. Does that make sense? So I said, right, when you write down this statement, you also need to ask why the limit exists. The answer is simple, because with this formulation, then the limit exists by law of large number and equals to that. Any question? And so this is also the reason why, right? We don't want here. It's okay. Law of large number also will have this divided by, again, in terms of infinite, right? Plus one here doesn't really matter. But I think the n here is a little bit more conventional to use. Any question? All right, so this is, right, the long-term proportion that a Markov chain spent at a state. But this long-term proportion has a very special property. So let's look at a theorem again. And by the way, right, so the context so far is that we have a irreducible Markov chain, right? We have an irreducible Markov chain. So you can think of a matrix P, n by n, where all the states are connected via some path. So because it's irreducible and it's recurrent, every state has a pi I attached to it. So pi I really is a vector. Pi itself is a vector. You can think of pi as a vector. Like that. Okay. Where each of the pi right now is 1 over expectation of time I, the return time, the average return time. But here's the proportion. Here's the proposition that basically pi times p is equal to pi. Hold on. Yeah, no, it's true. I mean, I'm wondering what the order of presentation I should give you, but yeah, this is true. Okay. So in other words, well, you know what? I should qualify this with some statement, but let's say this is only true for recurrent. So we have an irreducible Markov chain to begin with. All right. Because if it's transient, then the pi doesn't exist to begin with. But let's say that we have a recurrent irreducible. So what I want to say is like this. So basically, right, why would this equation hold? And then maybe we can make it more precise later on, right? With assumptions about positive recurrence later on. So the following is the reasons as follows. Why in general that we can expect this? So what's pi times p? What does this equation say? It says that pi times p, right, is row times column, right? Row times column. So that means pi I, p I j, sum over all I is equal to pi j. Okay, that's what we're saying. Now, why should this be true, or why must this be true? It's as follows, right? If you look at, let's say, if you look at a sequence, right, of states, let's say, right, let's just look at 3 states. Now, let's say you focus on pi sub 2, right? Well, clearly pi sub 2 is about proportion of times as the Markov chain is in state 2, right, divided by the total number of times, right? So let's just roughly say however, right, if you take a step back and see where these 2's come from, okay, you see that this 2 comes from the 1's or the 2's, and let's maybe throw in a 2 here at the end, like that, okay, and the 0's, right? So in other words, if you wonder where this 2 comes from in the long run, the 2 must be preceded by some other states, right? Or even by 2 itself. And then, right, from those previous state, then you have a chance to go to 2, right? In other words, it's like this. If you look in the long run and you wonder, okay, I look at the number of 2's, right? And I divide by n. Then I can categorize this number of 2's as the following. The number of 2's preceded by 0 plus the number of 2's preceded by 1, etc. And all of these divided by n. So I look at the number of 2's, but I also look at number of 2's preceded by some other state, right? that's fine because I just break it down to further categories. But how many of these are there? How many twos are preceded by 0? Well, if you think about it, right, the number of 2 preceded by 0 must be, right, depending on how many zeros there are to begin with. Because if you have a 0, then you might have a 2, right? So it depends on 2 factors. The first thing is how many zeros there are, how often the Markov chain is in state 0. So it's approximately pi 0, right? And then, so you can do something like this: n times pi 0. N is the total number of times you look at, right? The length here. So if you know that, right, among these times, 30% of them are state 0, then n times pi 0 will give you how many state zeros there are here. But of course, not all the state 0 will lead to state 2, right? Sometimes it leads to state 1, sometimes it leads to state 0. So n times pi 0, but also times p02. Does that make sense? So basically, right, it's a long-winded way to say that if you look at the number of times the state spent at a state, is equivalent to the proportion of time the Markov chain stays in some state that's previous to that state and then transition into the state. In other words, right, it's like this. So this is equal to, let's say, approximately n pi 0 times p02 plus n pi 1 times p12 plus n pi 2 times p22 divided by n. Well, you see, right, the n just washes out, and you have pi 2 is equal to pi 0 p02. Does it make sense? So that's sort of like the essence of the argument of why, if you have a long-term proportion, you have a vector that you claim is a long-term proportion, that it must satisfy this relationship. Okay, so far. Now, notice, right, one thing that might be lurking in your mind is that this is a probability vector. Probability vector, meaning that this should sum up to 1. Notice we never made that claim so far. Yes, and that's why I say there's some details here that should be made more precise. But as far as we're concerned, this could be just a vectors of all zeros, meaning that they're all null recurrent. And this is still true, right? 0 times p is 0. So the argument here is not about, so what I'm saying is this. This is not necessarily a probability vector. Meaning that, yes, each of the pi I is non-negative by definition, but I did not make any claim the sum equals to 1. Okay, right now, the meaning of pi I is just the long-term proportion that the state spends, that the chain spends at state I. And under that interpretation, we already have this relationship. Okay, so far. And of course, under some proper assumption, it will be a probability vector, meaning we will take on this property as well. But right now we don't have that yet. We don't need that yet. Okay. So now maybe let's point out two more things with this relationship, and then we'll kind of go back to it later on. The first thing is from a linear algebra point of view. Not that we will need to do linear algebra here. This kind of says that pi can be or may be a left eigenvector of P with eigenvalue 1. Why do I say maybe? The word maybe here refers to the fact that, you know, in this analysis, we may end up with pi being all zeros. And you know, an eigenvector, right, has to be a non-zero vector to begin with. So in other words, what I'm really saying here is the analysis of this equation is connected with the analysis of a left eigenvector with eigenvalue 1 of a transition matrix. It may or may not have an eigenvector, okay? And the case where it does not have an eigenvector may also correspond to all the pi's being zeros. Because with linear algebra, you do not allow for zero eigenvector. The second thing I want to say, right, is about how this is connected with the Chapman-Kolmogorov equation. So maybe I should not put all of this down in, right, that space. So pi p equals to pi has two observations. A, this is connected to the linear algebra analysis of the left eigenvector of P with eigenvalue 1. But the second one, so that's just something for you to think about if you want to investigate, right? This from a linear algebra point of view. But B is much more important here. Because if you remember the Chapman-Kolmogorov equation, it says that, right? Probability, let's say xt plus 1 equals to j is probability xt plus 1 equals to j condition xt equals to I times probability xt equals to I, and then sum of all I. Well, we can call this pi sub j at the t plus 1 time, right? This is the distribution of the Markov chain at time t plus 1. This is the sum of all I. This is pi t, sorry, pi t sub I, and this is the transition probability Pij, right? In other words, this is just saying the next probability, right, vector distribution of the Markov chain is the previous one times P. Notice here, we clearly identify pi sub t and pi superscript t and pi t plus 1 because they may be different. But here is the same vector pi that satisfies pi p equals to pi. So this is exactly connected to that question I say which we raised before. where possibly both of these converge to pi. So pi here, right, is referred to as the stationary distribution. Of the Markov chain. What it means, it takes on two meanings. The first meaning is that if you start at pi, then you will stay at pi. You will not move away from that distribution. But the second meaning is that, well, even if you start at any other distribution, you start with any other distribution, then eventually with time, you will converge to that stationary distribution. These are two different meanings, but they're kind of connected, right? So this equation has so many use and so much meaning, right, in terms of the Markov chain. So we're gonna analyze this, more and say more precisely when, it means what, right? But so to recap, right, this is many subtle points going on with this and these things. The first thing, right, is that right now, pi for us just means the average proportion of time the Markov chain spends in a certain state. Under that assumption, by looking at how, right, the Markov chain transition from one state to another, we can already derive this relationship, pi equals to pi. But this relationship does not make any claim on whether pi is a probability, all right? But it hints very strongly at that. And so the connection exactly is about the concept of positive recurrence, okay? Which we will talk about after we, right, resume next week. When we resume next week after the second midterm. All right, so I guess let's stop here today. So Friday, okay, is midterm 2, and then we're gonna, continue with our lecture on Monday.
Excuse me, Professor?
Yeah.
Could you scroll up to quiz 1 for me, please, real quick?
Mm-hmm. Right here.
Professor, could you also post the homework solutions if possible?
I haven't I?
Oh,
Which
sorry,
one?
let me double check.
We're good?
Will what homework will the exam go up to?
Last week.
So it'll include both parts of it?
Yeah.
Okay.
All right. So I suppose we're all good. If there's any question, feel free to send me an email. If not, well, see you on Friday, as the usual setup, and then you have the exam.